So I'll just introduce Dr. Shahar Boneh as a colleague of mine for some 20 years or more. Haven't fantastic statistician, and he's going to talk to us about the persistence of integers.
Okay, great. Thanks, Dave. Am I sharing my screen?
Not yet.
Not yet.
Okay. Oh,
maybe Katie can help.
I hit share screen. You don't see my screen?
No.
Not yet. You might need to pick which. Oh, hold on. I
There you
think
go.
it's coming.
There
Yes,
we
you
go.
can see your
Perfect.
screen.
Okay, very good. Thanks. Okay. Just a second. Oh, there we go. Are you seeing it now in a presentation mode?
Yes.
Yes, great.
Yeah.
All right. So shall I start? Okay, I guess it's time to start. So thanks, Dave, hi, Dave, again. So hi, everybody. Good morning. So I'm Shahar Boneh, and I'm gonna just give you a little modest expose talk about something I just learned a few months ago. So it's on the persistence of integers. So the background is, some of you who know me know that I'm not in number theory. So my area is probability and statistics. So I've been giving talks here for many years on mostly probability. But today I'm gonna deviate from my area of expertise, and I'll tell you about a problem I came across a little while ago, a few months ago. I heard about it from a friend on a Facebook group. So I'm in a Facebook group that exchange mathematical problems. So they showed me this problem and they asked me about it. So here goes. So it's about the persistence. So first of all, what is the persistence? I'm trying to, hold on a second. So the menu bar hides some of my screen. How do I get rid of that menu bar at the top?
You should be able to just drag it and move it around to wherever it's out of the way.
Oh, that way. Okay.
Shahar, I just see what is persistence and then a whole blank whiteboard, so I don't see anything hidden.
Okay, but do you see at the bottom? You see the menu bar at the bottom?
Yeah, with chat, share screen, and all that.
Okay. Anyway, let's see how it's gonna work.
If it hides one line or something, you can just
Okay. Okay. So I'll have to work around it. I'm not sure how to get rid of that menu thing. Anyway, so what is persistence? So in the plenary talk before, unfortunately I had a connection issue, so I was in and out, but I heard they use the word persistence. So I'm not sure if it's in the same context as I'm gonna say. So the persistence of an integer, non-negative integer. By the way, I'm curious, have any of you heard this concept, persistence of an integer?
I have not. My degree was in number theory.
Say again?
My degree was in number theory, but I have not heard of this.
Oh, wow. Wow. So in that case, okay, because I was wondering if it's how well known it was. When I first heard about it a few months ago, like I said, it was new to me too. Anyway, so what is the persistence of an integer? It's the number of times that we have to multiply the digits of an integer until the result becomes a single digit. So you take an integer and start multiplying the digits into themselves. And you keep doing that until you end up with a single digit. So for example, what is the persistence of the number 39? So here it is. So 39, you go 3 times 9, 27. So now you take 2 times 7, 14. You take 14, 1 times 4 equals 4. And now you have a single digit. So how many times did we have to multiply? 3 times. So therefore, the persistence is 3. So the persistence of a 39 is 3. So guys, I hope this is clear. Now, so this means, for instance, for starters, that the persistence of a single digit integer is going to be 0 because you don't have to multiply at all. It's already single digit. And the persistence of the numbers 10 to 19, the integers. I mean, I'll use the word numbers for integers. I'll just call them numbers. So 10 to 19 is 1, because it's pretty clear. You multiply once and you get yourself a single digit. And that could be a 0, by the way. And we can easily see also that the persistence of all the numbers between 20 to 24 is also 1, right? Like 23, 2 times 3, boom, you got a 6, single digit. And so if you think about it for a sec, you realize that 25 is the first time, is the first number that has a persistence 2. Like 2 times 5 is 10, and then 1 times 0 becomes a 0, right? So I thought that's a pretty cool notion. So let's see. By the way, I need to go back just a second. Oh gosh, you see, this thing is hiding stuff for me. So the persistence of 25 and 2, and so is the persistence. There's no way to get it out of the way. It's very annoying. Anyway, so the persistence of 26 to 29 is also 2. But when you get to 30, it becomes back to 1, all the way to 33, right? So, yeah, there we go. Now that's so the first thing we notice is that the persistence is not monotone in that sense, which means once you get to a persistence 2, you don't necessarily stay there, you can go down to lower persistence. That's pretty very intuitive. So, and as a matter of fact, the number 39 I just showed you is the smallest number with persistence 3. So it goes 2, 1, 2, 1, kind of flips around until 39 is the first one with 3. So at that point in the group I told you about, they asked me, what's the smallest number with persistence 4? So that's the question they posed to me. So it sounded pretty intriguing. So I went for it. And of course, how would I go for it? I went brute force. I started to check number by number after 39. Clearly, I could skip the 50 or 60 because they just multiply into a 0. So I went on and on and on until I found the number with persistence 4. So what is it, do you think? So let's see what it is. The number was so the number with persistence 4 is 77. That's the smallest number with the persistence 4. So let's check real quick. 7 times 7, 49. 4 times 9, 36. 3 times 6, 18. 1 times 8, 8. There we go. So we have to multiply the digits 4 times until we reach a single digit and a result with a single digit. So guys, that's a pretty interesting notion. And so I thought it's kind of interesting notion. And then I was challenged. What's the smallest number with persistence 5? So, so how much work am I going to do here? So at that point, I realized one thing. So I said, first of all, I'm coming up with a theorem. Again, regarding how monotone this persistence issue is. So I've seen it's not monotone in the sense that once you hit the persistence, you stay there and on, but it's monotone in this sense. The smallest number with persistence k plus 1 always going to be greater than the smallest number with persistence k. So that's a theorem. So which means if I'm looking for a number with persistence 5, and I know already that 77 is the smallest one with persistence 4, I can start looking from 78 and on. So right, so that's what it is. So I said, so now how do I find this number with persistence 5? So then I realized it's going to be a really labor-intensive job to find the smallest number with persistence 5. I began to start working, multiplying. I got 78, 79, et cetera, et cetera. And by the time I got to nearly 200, I said, no, I'm not gonna, I might end up spending a lot of time here. So it's really labor intensive. So of course, at this point, someone might say, we'll see what someone might say, but first of all, so that of course raises the general question. what is the smallest number with persistence k? And the answer, it's not a feasible way to answer it manually. There's no way to answer it. So you say, well, not manually, but we can do it on the computer. We have technology these days. So yes, absolutely. So one can write a program in Python or any other programming language to find the persistence of any number, and therefore, consequently, the smallest number with persistence k. So by the way, what I'm telling you one thing today is that this can be a good exercise for students in Python programming. Actually, Mathematica has a built-in function, which is called digit product. I don't know if any of you who use Mathematica were aware of that, calculates the product of the digits of integers, so we can do that on Mathematica as well. But I was interested in asking, I asked myself, is there a systematic way other than brute force or by computer to find the smallest integer with a given persistence? So what's the smallest integer with persistence? 5, 6, 7? Is there a system here? So I couldn't find one, but I'll share with you in the next minute a couple of insights. First of all, obvious insight. So suppose you want to go other than brute force. So I know 77 is the smallest with persistence 4, and now I'm searching for the smallest number that has persistence 5. So if I go one by one, brute force, so obviously how can I do better than brute force? So check one by one. Skip all the numbers that contain 0. Guys, is that pretty obvious? Yes. Is a little less obvious? Skip all the numbers that contain the digit 1. Why? I'm looking for the smallest number with the next persistence, with persistence k. Because if a number contains a digit 1 and has a persistence k, I can just knock out the digit 1, get a smaller number on the same persistence, right? So there's no point even checking out anything that contains 1 anywhere in it. Another interesting insight I came up with, avoid any numbers that contain both 2 and 5. You don't have to check them. Why? Because if it has 2 and 5, you multiply them, you get a 10, so the product of all the digits will be a multiple of 10 and will contain 0 and will terminate on a second step, become 0. So it has any, so here's a theorem. The persistence of any numbers with digits 2 and 5 is at most 2. I hope it makes sense. So I ask, is the set of all integers with persistence k finite? And the answer is no. We can always add another digit 1 at the end and have the same persistence, have a bigger number with the same persistence. So those are infinite sets per each level of persistence, infinite sets of integers. So it was really interesting insights. I kept looking for more systematic ways to find the next number with a small, the number with the smallest number with persistence k. Here's another insight. If 2 different integers have the same digits, in different orders, like 329, 932, then they will have the same persistence, right? Because the product of the digits will coincide right at the first step. Like here's the example, 329, multiply the digits, you get 54, 932, multiply, get 54, you end up with both have persistence 3. So all integers with the same digits, including the repeating digits, will have the same persistence. Among those, among those, the integers that has the digits in ascending order will be the smallest, right? So for instance, 3,447 is smaller than any whatever numbers that have those same digits, but not in ascending order. So the conclusion, we only need to check integers that have their digits in ascending order. That saves a lot of work. You see, so I really liked how this insight saves me a lot of work. So guys, finally, here's the answers. So has been run on Python. And here are the answers. So the smallest integer with persistence 5 is 679. Well, it's a good thing I didn't keep checking. I stopped at 150. And the smallest one with persistence 6 6,788. And it runs up really quickly until when you get persistence 9, you're in 26 million something, and then billions, and then 11 is in the several trillions, many trillions. So, wow. So that goes up quickly. And notice I stopped at 11. So if someone asks me, what about persistence 12 or more? How do you find the smallest number there? Guys, are you ready for an interesting surprise? So other people, not me, ran the same computer programming, and they checked up to integers with 20 million digits and did not find any number with persistence greater than 11. So guys, here's a conjecture. There do not exist integers with persistence greater than 11. So 11 is the largest persistence there is ever. I found it amazing. Wow. So, and proving this is currently an open problem. So that's why it's a conjecture. So I've seen several papers talking about it. And this is an open problem right now. Prove that there do not exist integers with persistence more than 11. 11 is the highest possible persistence. Kind of interesting. So obviously I say, maybe I try to prove it. So my approach, I said, I'll try this approach. Turn the problem around. Instead of asking what's the smallest number with persistence k, how do we find a number with any given persistence, which is more than the smallest one? Suppose I tell you, find me a number with persistence 10. How do you do that? Now, if I'm able to construct such number, maybe I have the key to proving that there is no way to do more than 11. My direction is prime factorization of the digits. I'm pretty much out of time, so I'll do it in 1 minute. So for instance, what I mean is consider the example of like two integers, 479, 667. Both have persistence 3. But notice, both become identical after the first multiplication of the digits. Is that a coincidence? No. What's the reason? The reason is that those two numbers have the same prime factorization of their digits, not the numbers themselves, but of the digits. So 479, 4 factors 2 and 2, 7 is 7, 9, 3 by 3. 6, 2 times 3, 6, 2 times 3, 7 is 7. So list all the prime factors here, one by one. They have the same prime factors of the digits. Interesting, isn't it? So my theorem, my lemma or starting theorem is, I haven't proved it, it's also a conjecture. Integers with the same prime factorizations of their digits will always have the same persistence. So I wondered, is this the key to proving that there is no persistence more than 11? I tried. That's as far as I could figure it out. As I doubt if I'll be able to prove that because I'm not a number theorist. I don't have enough experience in number theory. So, but I do have another conjecture. For any k between 0 to 10, the set of integers of persistence k do not contain digit 1 is finite. So if you drop the digit 1, you can always add ones, therefore it's infinite. But if you exclude the digit 1, those are finite sets for each persistence. Still, open problem, no proof. No one knows how to prove this. Kind of interesting. And the other extension, 1 second. So I just want to mention that this is also known as multiplicative persistence. There's also the concept of additive persistence, like adding the numbers until you get single digits, adding the digits, or other operations on the digits. And of course, you've probably been thinking, this whole thing depends on being in base 10. So I only refer to base 10, so we can extend that to any base and you get really interesting results. Like for instance, if you're in base 3, the maximal persistence that you can get is 3, and that can be shown. So another interesting question is, in base n, what's the maximal persistence in any given base? And if somebody wants a really cool problem to give their students and torture them, find the smallest prime number with persistent k. By the way, there is an answer to that. You can write a code for that. It's a lot more, it's a little bit more complex code, but it's interesting. And the interesting thing, at first, those are very different. Like with persistent 3, it was 39. The first prime, though, is 47, and so on. So that's it. Whew. So, guys, this is it.
Thank you, Shahar. I see there are a couple questions on the chat.
Okay,
Anybody want to speak up on those?
go ahead.
Oh, well, I had asked a question, but you answered it already.
Okay.
I would just mention, so the persistence class, that does partition the integers or positive integers into equivalence classes, correct?
Yeah. Yes. You might.
So-
Yeah. That's the idea. So it's disjoint classes. That's right.
Yeah. So some of those, I mean, because we have an infinite collection, some of those equivalence classes have to be infinite.
Yeah, the last one is the one 11. The 11 one is infinite. So therefore, when I say it's finite, I said up to 10.
Oh, I see. Okay.
You see what I'm saying? So yes, so up to 10. Obviously, the last one, the one that the 11 that there's no greater than that, that has got to be infinite. So for sure. Now, if you include ones, notice if you include you allow any numbers, each class is each group subgroup is infinite. The conjecture that talks about finiteness is the one that says consider all the integers that don't include the digit 1. So that's the conjecture. Up to 10 are finite, 11 or more infinite. Wow. Okay, doc. Thanks. Am I still sharing the screen?
Yeah,
Yes.
but it's not in present mode anymore.
Okay.
I
So-
feel like we could construct an infinite family of persistence 2.
Mm-hmm.
Wait, you're not allowed to use zeros or ones in your conjecture.
Yeah.
Okay, never mind. I take it back.
Okay. And by the way, what was the other question that I already answered? I just wonder.
Oh, the question I had asked earlier was, do we know that given k, is there guaranteed to be a number with persistence k? And then that certainly your conjecture would say no.
Yeah, that's right.
Yeah.
That's right. It's amazing. There is persistence for every number, but it stops at 11. I found it really amazing. I couldn't stop thinking about it. All right. So
Super interesting.
I have
Thank
one
you.
more question.
okay, one more question. Okay.
Why does Mathematica have that function that you referred to, the digit product? Why
Yeah.
would that be built into Mathematica?
Why not? I have no idea. I have no idea, but you might think, why not?
Sure, why not? But I just wonder if this is a useful tool in other contexts.
Oh, you know what? I don't know that. I've never seen it being used in other contexts. No,
Okay.
I wouldn't know. I don't know. Yeah, it's kind of cool. So yeah, but you raised, and by the way, Python has a function that you can break an integer to an array of its digits. So it's built into Python. So that's also interesting. Is that it?
Shahar?
Yeah.
Shahar? I had a question.
Okay.
It's about your theorem about prime factorizations.
Uh-huh.
Have you seen a number with persistence, a given persistence, say persistence 5 or something like that, where they had two different prime factorizations? Like one had one, like, you know what I'm saying? You showed two numbers that had the same prime factorizations and they got the same, obviously they had the same persistence.
Yeah.
But have you found another one of persistence, that same persistence with a different prime factorization?
Oh, so you're asking, is that an if and only if?
Yeah.
So you know,
Seems like there should be there might be, I mean, just from your computer, like just running the test for them, that'd be an interesting thing, because if there's only one, then that would suggest that would have a finite number in there, because there's only so
You're
many
right.
different ways you can break apart a prime factorization.
Yeah, that's right. Yeah, I'm gonna share that one. You're quite right. Is it sharing? Don't know. Do you see my screen to see that factorization? Now, but notice I'm hesitating to answer your question, because you know the factorization is not of the number itself, but of each of the digits of the number.
Yeah, but there's only so many ways you could, I mean, because that's finite. So
That's
there's,
right.
I mean, there's only so many ways you could break that down and disclude ones.
Yeah, you
But
know,
I'm saying,
I
like,
don't know.
if you had a list of all the ways that you had persistence 4 or whatever that is that 4?
Yeah,
Then you could see, it's like, oh, is there another one with a prime that had a prime factor of like 11 in there? And
yeah.
23
You know,
or something like that.
yeah, you know, I'm pretty sure that there are integers with the same persistence with different factorization. I'm pretty sure it's not.
Okay.
I'm pretty sure it's not. So, yeah. Otherwise, it would be. No, I cannot. Yeah, I'm pretty sure, because yeah. You know, I'll look for one. I'll look for an example for that. It's a good point.
Come across the hall and we'll talk about it, because
Yeah,
pretty interesting.
yeah. It's a good question, though. It's a good point.
Or you could even just limit the number of, sort of a partial if and only if, you could limit the number of prime factorizations if you throw out all the ones and the 2-5 combos and all that stuff. Other questions? This is a great problem.
So basically, that's an approach I'm trying to. Yeah. Anyway, so I hope you found it pretty interesting. I thought it was pretty interesting. Thanks. Are there any other questions?
All right, well, let's thank our speaker. Yay. Thank you, Shahar, for a great talk and a very interesting problem.
Yeah, thanks, Dave.
Yeah,
thanks, everybody.
That was really fun.
Yeah, thanks, everybody. Yeah, thanks. Bye-bye. Here. See you in the next session.
Don't forget, Dominic is speaking at 1 o'clock, right, Dominic?
Yeah. So what's now? So what do we have now? We have
So now we have a break until 12, I think.
Yeah, okay. All right.
Yes,
Cool.
the next session will begin at 12, and I just pasted some additional links for the other sessions in the chat. But thank you so much. That was fantastic, and we appreciate everybody's time and questions.
Thanks. Am I still sharing? I don't know how to stop sharing.
You are still sharing.
How do I stop?
Down at the bottom, I can actually stop it for you. I'll do that.
Okay. All right. Thanks.
Thank you.
Thanks. It was cool. Thank you so much.